In the first video, we looked at the basic definitions and terminology in redox reactions and look at how to use the table. So we're just going to look at which of these points we have not covered yet. We've spoken about standard conditions. It's 25 degrees, 1 atmosphere for gases, and 1 mole per cubic decimeter for solutions. We haven't really spoken about hydrogen. Now, if you look at hydrogen, the way you will see here that all these reactions was written down as hydrogen as the reference. So basically it was connected to a hydrogen half cell and these values were determined. Now if you look at these values, if the ones at the top, remember, would then be stronger reducing agents, meaning they will rather be oxidized. They will give off electrons. They will then give off electrons to the hydrogen ion, which will take them up, meaning they are being reduced. So then hydrogen will be your oxidizing agent. If hydrogen reacts with anything below, then hydrogen will be the reducing agent, meaning again it would rather be oxidized, so it will give off an electron to something that would rather be reduced and be the oxidizing agent. So that something will then take up the electron. So it's either going to be a reaction happening like this or a reaction happening like this. Now, if you look at these reactions, these values are all negative above hydrogen because these substances would then rather lose electrons and the hydrogen would rather gain an electron. But if they have a positive value, hydrogen would rather lose the electron and those substances will rather gain the electron. So the more positive value, the bigger the chance of the substance taking up an electron. And we said that before because we said an increasing oxidizing ability, which means a stronger oxidizing agent, would rather be reduced, taking up electrons. Now, when we look at the cell notation a little bit later, you will see that hydrogen is the only one that's a bit of an exception because hydrogen here is written in a specific way, and we're always going to write the hydrogen reaction as the anode reaction, as if the hydrogen undergoes oxidation. So it will always be your anode half reaction, and you can basically almost memorize it because you're always going to write it in this way. Now, the standard electrode potentials, we've spoken about how they could be determined. So you can use E0 cell, that little standard just means standard conditions, cathode minus anode, and we've spoken about this. If it's a positive answer, we know that it's a spontaneous reaction under standard conditions, and if it's a negative answer, then it would be a non-spontaneous reaction. So these points we've covered. Now we're going to look at galvanic cells or spontaneous reactions. Now in a galvanic cell, we're going to just skip here quickly. We know that it's a spontaneous reaction, so chemical energy would be converted into electrical energy. Please know they always ask these energy conversions. So what you need to be able to do is decide which one is oxidation and know that oxidation happens at the anode. Remember, an-ox. And then you must decide which one will be reduction, and reduction happens at the cathode, red cat. You'll remember that picture of the red cat on the ox. All right, so then we're going to write these half reactions and we're going to write an overall cell reaction. And normally we're going to show that using the ionic equation. And that's what we did also in the previous lesson. Now we are actually going to look at a galvanic cell and then we'll come back to these points and see if we've covered everything. Now in a galvanic cell, a normal galvanic cell, you would have substances. So you'll get a question like this and you wouldn't know what's going on. So your first step would be go and determine what substances I have. Now one important thing that this diagram doesn't show is that aluminium ions cannot be picked off a shelf. Remember, it's in solution, it's aqueous. So there will be some form of spectator ion, so aluminium sulfate, aluminium nitrate, aluminium chloride. There will be some negative ion in this solution as well. Same on this side. Lead cannot just be here. It comes from something, a solution. It's an ionic salt. So lead nitrate, lead chloride, lead something. So please remember that if they can ask you for a suitable electrolyte, so all you then do is add a negative ion to your positive ion and you have it. In this one, we don't have gases. Please remember, if there are gases, gases need an electrode. Here, the aluminium is used as the electrode for the aluminium solution. That doesn't have to be the case. You can use anything that can conduct electricity if that electrode doesn't take part in the reaction. And here we've got lead at the lead electrode. Again, it doesn't have to be. Once we've decided on the oxidation and reduction half reactions, I'll get back to that. So your first job is, and I would say do it even if the question doesn't ask for it, because you will see once you've got your oxidation and your reduction half reaction, you can do anything. So now we need to decide. We've got aluminium and aluminium ions. We've got lead and we've got lead ions. We haven't really spoken about these ions, but we can go find them if we want to. There's NO3 ions that are in this solution here that we now going to call the salt bridge, and we'll get to that. And we've got our sodium ions here. I'm not going to go into the detail of why we need it, but you've got all the small videos. So if there's any part that you don't understand, please go and watch those detailed videos again. So the salt bridge is here to close our circuit, because remember we did direct transfer first, but that doesn't give us electricity. So we needed the electrons to move in a wire so that we can actually have electricity. And you can see now we've got a reading on our ammeter here. But let's start. Oxidation we need to find, reduction we need to find. And to do that, all we have to do is go back and look at our table. So if we go and look at our redox table again, we're going to find aluminium and aluminium ions. So you just highlight them. Oops, I'm just making them white. So there's aluminium. We've got aluminium ions as well. Then we've got lead. And we've got lead ions as well. Remember I said we do have some nitrates as well. It could be Cls, it could be anything else, but in our solution, we decided that it's just nitrate or sulfate. But remember that for these ions, we need hydrogen, and nowhere did they say that we have hydrogen available. So those half reactions are not available for us to use. We also have potassium. So we can actually go and mark the potassium ion there, because that could be part of the reaction because it's there. So now let's go back. So we need to decide what is going to be our oxidation reaction and what is going to be our reduction reaction. And you follow the rules from the previous video. The strongest oxidizing agent would rather be reduced. So the lowest one here, which is my lead, would be my reduction half reaction. And I'm going to write it from the left to the right. And then we're going to say the strongest reducing agent would rather be oxidized. And therefore, it's going to be my aluminium. So aluminium is going to be my oxidation half reaction, and lead is going to be my reduction half reaction. So now we can go and write that. So oxidation, you write it straight from your table, Al, and you can look at your table again if you forget. There's Al that forms Al3+. So Al, aluminium atom, is going to form Al3+, and we've got given off 3 electrons. Now our reduction half reaction is Pb, 2+, that takes up 2 electrons, and we form Bb. Now I've done the balance, writing the net ionic equation, but let's just do it again. You have to change them both to 6. So to change that to 6, I'm multiplying by 2 and by 2. To change that to 6, I'm multiplying by 3 and by 3. Then all you have to do is write the left-hand side. I'm going fast because we've done this before. 3Pb. And on this side, we've got 2Al plus 3 Pb. But please remember, if I write Al, it's going to be wrong. It's Al3+. You need to be very specific. And in this one, you need to say Pb2 plus because ions and metals are not the same thing. So you need to be specific. Now, we can identify a lot of things. We can say, what is, remember, for the oxidizing agent, we're going to look which one was reduced. So the lead 2 plus, and be careful, you have to say lead 2 plus, not lead. The lead ions will be my oxidizing agent because my oxidizing agent is reduced. We could look at my reducing agent that is oxidized. So aluminium is my reducing agent because it is oxidized. Please don't talk about the product. Your oxidizing agent and reducing agent must always be your reactants. So there we have that already. Once we have our reactions, we can go back and get our E naught value. So our cell potential will tell us whether the reaction is spontaneous or not. And if you go and work this out, you will see that it is spontaneous. Now, what's also important here is that we can understand the whole cell by looking at this, because now we know that aluminium here is going to give off electrons. So electrons are given off on this side. If there's an excess of electrons here, this side becomes negative and repels electrons, and they will move through our wire where they are being taken up by the Pb2 plus ions. So on this side, electrons are being taken up. Now we know already that where oxidation takes place, we're going to call the anode. So this side where electrons are given off will be called the anode. This side where electrons are taken up will be called the cathode. We don't really say that they are charged. They do behave almost like something that has a charge because I'm forming extra electrons here. So this side becomes a little bit negative. But just remember they're not charged. We don't have an input of electricity here. The conversion is chemical energy to electrical energy. So in these wires, I have electrons moving. Please remember electrons do not move in liquids. All right, so that gives us our path of the electrons. Also, if this is a voltmeter, please remember voltmeters have very high resistances and therefore currents cannot flow. So this has to be either an ammeter or a light bulb for a current to flow. Now, you can also already see that on this side, my Al3 plus concentration is going to increase because I'm forming positive ions. So on this side, my solution will become a little bit positive. You can see that on the reduction side, I am using my positive ions. So whatever the negative ion was that was in there, that's going to be in excess. So why did I say decrease negative? So this side is going to be a little bit negative because it's now got an excess of negative ions because my lead ions are forming lead, neutral lead. Now that's my second function of my salt bridge. Because the solution becomes a little bit positive and electrons wouldn't want to move away from a positive, it will cause the negative ions from my salt bridge, and we normally use a nitrate because they're always soluble, and we normally use a group 1 metal because now if you look at our table, the potassium, sodium, they're all high up in the table, so they didn't really take part in this reaction. So they didn't interfere with our reaction because they are weak oxidizing agents, and therefore the lead was rather reduced. So that's another thing that the two half reactions tell you, which way the ions would move. On the negative side, I will have my positive ions moving there because I want to keep this electrolyte neutral. So my salt bridge firstly closes the circuit and secondly keeps my two electrolytes neutral. The next thing I can see from my two half reactions is how are these concentrations going to change? They often ask you about the concentrations. Now you can see that the aluminium concentration here is going to increase and your lead ion concentration is going to decrease. So that means that if you look at your table, I don't have standard conditions anymore. And that is important because now if I don't have standard conditions anymore, my value of my cell will change. My E cell will change. So let's look what we said. We said aluminium, the ion concentration is increasing. So therefore, this value will go this way because the concentration is increasing a little bit. If you look at your lead ion concentration, yeah, I'm forming more of these, but this ion concentration is decreasing. So therefore, I'm going basically almost back up here. So because of the changes in the concentrations, my E value will now decrease. Because if you fill it back into the equation for my cathode half reaction, the value will become more negative, and for my anode value will become less negative. So you will end up having a smaller E cell value, and we don't want that. So as the concentrations decrease, the E value will also decrease, or decrease and increase. The E value will decrease, and that means that eventually I'll have no voltage, and that's basically when your batteries run flat. There are little equilibriums happening everywhere, and if you want to look at the equilibriums in more detail, please go and look at those videos, because they can ask you what is going to happen if I increase the Al3 plus concentration, for instance. So if I increase the Al3 plus concentration, it's going to mean that if you look at it as an equilibrium, the reverse reaction will be favored. But if you look at your table, it means that your aluminium concentration here is going to be increased. So let me just do that. So if my aluminium concentration is increased, that means this value here, this concentration, it's going to become an increased oxidizing ability. So this value will become less negative. And if you put that in your E cell again, that means that your E value will decrease. But if I go and increase the lead ion concentration, you can see that will almost in inverted commas favor the forward reaction. But again, if I look at my table, if I increase the lead ion concentration here, I am now going to give this a more positive value, because now it's going towards the positive side, and you will see that it actually is going to increase my E value. And that is often asked, how does the increase in the solution concentrations affect your E value? Okay, in this one, we didn't have a spectator ion, but like I said, it could be chloride, nitrate, anything like that. Please just look out for silver. Silver chloride is a solid, and therefore don't use chloride as your spectator ion if there's silver available. But nitrate is a safe one to use. Just use silver of nitrate because it's always soluble. All right, so we have predicted the oxidation and reduction half reaction. We've done an ionic equation. We've identified the oxidizing agent and reducing agent. We predicted that where it will take place. And we know that this is a spontaneous reaction because it's got a positive E value. The spectator ion you must be able to spot, and that would be the one that does not take part in the reaction. For instance, nitrate, sulfate, those ions. Let's look here. We have predicted the half cell. We've predicted the movement of the ions through the solution. We've predicted the electron flow. Please, observations. Now, the half cell even tells you this, because you can see that on the aluminium side, the one that loses electron, little pieces of aluminium is changing into aluminium ions. So this electrode will actually lose mass as well. So the electrode that undergoes oxidation will lose electrons as well as mass. Where on this side, you can see from the half reaction that the lead ions will be forming lead. So these ions are going to cling here on this side, meaning that this lead electrode will be gaining mass. So you would be able to see actually lead forming here, and here the lead pieces will be broken off. So this electrode will decrease in size. Also think about copper, because copper ions, Cu2 plus ions, are always blue. So if copper ions are forming copper, the blue color will disappear. So just keep that in the back of your mind. We've spoken about the salt bridge. We know how the salt bridge keeps it neutral because the positive ions will stop the one solution from getting negative, and the negative ions will stop the one solution from getting positive. And we know the energy conversion. That brings us to writing the cell notation, and this is your biggest job. So we need to look at how to write the cell notation. Now, again, if we have our half reactions, which we do, and I'm actually just going to take this cell and take it over to the other side that we have it there. If we now have our cell and we have our two half reactions, anode and cathode, what you basically do when you write the cell notation is you give a shorthand method of what is going on without drawing the whole picture. And these points are all in your notes and you have them here to go and look at as well. I'll make it neat again after. But what I want you to see is that you're basically going to start by writing the salt bridge in the middle. We do a double line for the salt bridge, and on this side I'm going to show my oxidation half reaction, and on this side I'm going to show my reduction half reaction. Oxidation we had as our aluminium reaction. So all you're going to do is you're going to say aluminium that was a solid changed into aluminium that were into aluminium ions. So you have Al solid changing into Al3 plus. We don't have to worry about the balancing at all in our cell notation. Now, if these two things, and you read your question and see if they want phases or not, if these two are in different phases, we're going to put a solid line between them. If they are in the same phases, and that's why one of your rules, then they will be separated by a comma. Please remember that. If this was something that cannot conduct electricity, so say it was a gas or two AQ substances, so two ions, then we need an electrode. And a very good electrode, and you'll see it's even used for the hydrogen half cell, would be platinum. Now, why platinum? Platinum is a very unreactive metal. It doesn't interfere with most of your half reactions. It also conducts electricity very well, so that's why it's a good electrode. And sometimes it catalyzes the reaction. So for some of the gases, it acts as a catalyst. So there's quite a few reasons why platinum is a good electrode to use. If you would use platinum for this one, you would just go and say platinum, and because they're in the same phase, here you would put a comma. But aluminium wouldn't need another electrode, so that's a bit redundant there. It's only if you have something that cannot conduct electricity. Remember, electrons cannot swim, so you need a metal for them to be transferred. Now, for solids, there's no conditions here, but for AQ substances, you have to write 1 mole per cubic decimeter to show that that is the standard conditions. Again, read your question and see what they want. And that's the one side done. On the other side, we have reduction. So on the right-hand side, always reduction, and you do the same thing. We started with Pb2 plus, we ended with Pb. So you're going to start with Pb2 plus, and you're going to end with Pb. Then you just think this one is AQ, this one is solid. They're different phases, so I'm going to put a straight line between them. If I needed another electrode, I would add it here, same phase, comma, different phase, solid line. But I still have to say for the AQ substance that it is 1 mole per cubic decimeters. If there was a gas, you would have to say that it is at 1 atmosphere. And then somewhere, please, next to this, you have to say that it happens at 25 degrees Celsius. And that is how we write this standard cell notation. So please, if they ask you for cell notation, don't go and write a chemical equation. A chemical equation has this plus this arrow forms this. And that is not what they're asking for if they ask for the standard cell notation. So please don't go and do that. So quickly, the oxidation on the left, reduction on the right. Extra electrodes will be written outside are they either on the left if it was oxidation or the right if it was reduction. A single line is when they are in different phases. A comma is if the species, they call chemicals, all these chemicals are called species. The salt bridge is two vertical lines in the middle. You don't have to show what the salt bridge is made of. That will be asked in a separate question. Spectator ions are not shown, and the balancing will not be shown. I've spoken about that. So here's an example of what it looks like. What do I start with? What do I form? What do I start with? What do I form? And then you can look at these examples. These were all in different phases, so solid lines. If there is a gas involved or ions that don't have their own electrode, you'll put the electrode on the outside. Um, Otherwise, you'll put a comma if they are in the same phases. Very important. Oh, I'm missing out number 9. Put the standard conditions if the question asks for it. If the question doesn't ask for it, you don't have to put it. If you're not sure and the question didn't state anything, then just rather put it. So now number 10, remember hydrogen I've spoken about is the standard electrode, and that will always be written as the anode. So it's always going to be written on the left-hand side of your equation and always in this form. So please remember that hydrogen is your standard half cell, and that is how it will be tested. So always it will always be the one that determines the electrode potential of the other substance. So we've covered all those points. Now, if we look at galvanic cells, remember they're giving us current. That means that if they're giving us current, remember current is Q over T. So it's electrons in a specific time. So if I want more current, I need to have more electrons flowing. So if there's an equilibrium or the reaction has stopped, there's no electron, so my current will be 0. Please remember that. For Le Chatelier, that's basically what I quickly showed you earlier. If I have an equilibrium, if I change the concentration of the reactants, that's on this side of the equation, if I up this concentration, remember, almost you can say the forward reaction will be favored and therefore the E naught value will increase. If I increase the concentration of my product, the reverse reaction will be favored and therefore the E naught value will decrease. But it is better if you go and look at your table and see what the increase in the concentration will do to your E naught value, and then you can calculate it, and the maths will prove to you that the E value will decrease or increase. Now, the last 2 points here is always asked. If you want to increase the current, now remember, if we look at our cell, let me just put it back here again, seeing that we have it. So if I look at my cell again, the place where electrons can be transferred is everywhere here where the liquid is in contact with my electrode, and everywhere here where the liquid is in contact with the electrode. So if the surface area of this electrode is made bigger, that more of it is in contact with the liquid, then I will have more electrons moving, and that means I'll have a bigger amount of electrons per unit time, which means my current will go up. The same thing with the salt, but current going up does not mean my voltage goes up. Remember, the voltage depends on the chemicals, a chemical energy that is converted into electrical energy. So to change the energy, I need to change my chemicals, or I need to change my standard conditions. Those are the only 2 ways I can change the energy, which is the EMF. Either changing my chemicals or changing standard conditions. Now, if I look at the salt bridge, this is basically a whole battery, if you think about back to electricity. Now, if I can make it easier for electrons to flow, it means my current will go up because I'll have more electrons per unit time. So if I make this salt bridge very short, okay, and give it a big surface area, so that means a short, fat salt bridge, then there's going to be less internal resistance. If there's less internal resistance or any resistance, then you know that it's easier for the electrons to flow, like you always use in current electricity as well. Less resistance, higher current. But again, it will not influence my EMF of my cell. And that is important. So the only way, and that is not written down here, the only way you can increase the voltage of your cell is by changing your chemicals or by changing standard conditions. The way you change your current is by increasing the surface area of your terminal so that there's more contact points for electrons to be transferred. But those electrons still have the same energy because they get them from the chemistry. And you can make a wider, shorter salt bridge, which means it's easier for the ions. Oh, I think I said electrons earlier. Remember, only ions move in liquids. Electrons will find it easier to move in the wire. Ions will find it easier to move in the liquid. So ions would find it easier to move here, and therefore the internal resistance will be lower, and that means that there would be a greater current. But again, the electrons still have the same amount of energy because they get their energy from the chemicals. So if it's the same chemicals, it's the same energy. And that will then bring us to the non-spontaneous cells.